How's it going, everyone? Thanks for tuning into my lesson plan. Today we're going to be talking about primary flight controls. What are they? How they work? How they help us safely fly an airplane? To get going, just a few things that you're going to need. There is a PowerPoint that I attached that has all the figures in it. And so that will be referenced throughout the presentation. They say a picture's worth 1,000 words. And they'll help us out. Just to start off, our objective today is to develop a high understanding of primary and secondary flight controls, how they control all three axes, and how secondary flight controls supplement and support the primary flight controls. Attached to my lesson plan is a video of I think it's a Falcon that had a primary flight control failure. It definitely looks like the rudder and ailerons went bad. It's having some Dutch roll and then some uncontrollable banking. That's definitely scary and will definitely scare you into thinking that, all right, maybe we should understand these primary flight controls a little bit more, just to be able to know if anything goes wrong. It's also good to know just how the airplane works in general. To start off, let's just start off with a couple of definitions. Get my stuff together. Pen. Perfect. Let's start with flight controls. What are they? How do they work? Flight control is easy. It's just how the pilot controls the direction and attitude of the airplane. It what goes from your hands to the structure of the airplane and how that all works together, and then from the structure of the airplane to the air around it, changing lift and everything to actually move the airplane in 3D space. So to start with flight controls, we have two basic flight controls. We have the primary flight controls and we have our secondary flight controls. Primary flight controls is the main means of controlling the direction and attitude of the airplane. And on most airplanes, there's three of them. There's the ailerons, rudder, and elevator or stabilator. Secondary flight controls are, the technical definition is improving aircraft performance, characteristics, or to relieve excessive control loading. So it's to, some examples are flaps, slats, spoilers, and trim devices. And so flaps, they increase performance, they increase lift, and allow us to come in at a steeper bank or have a higher angle of attack for a given airspeed. And then trim allows us to have the airplane on a lower control input on the airplane and be able to take some of the pilot workload out of it. Going back to a basic airfoil shape, let's talk about just a few definitions like chord line, angle of attack, and camber. And so here we have looking at figure 1, we have just an airfoil. We have as the air flows over it, we have our high pressure side and our low pressure side. Flip that around. Low pressure's up here, high pressure's down here, creating that lifting action. Our chord line is that drawn through the middle of the wing from the leading edge up front to the trailing edge in the back. And the angle of attack is how that chord line meets the relative wind that's coming in. So a higher angle of attack, just imagine this airflow tilting up and the wind's still coming from the same direction. Low angle of attack is the opposite. The camber of the wing is the asymmetry, technical definition, the asymmetry between the two acting forces of an airflow. So how the high pressure side and the low pressure side are different. So adding camber is basically changes the angle of attack, and taking away camber also changes the angle of attack. Changing camber means changing the angle of attack. Changing the angle of attack changes the lift and drag. And so if you one way to change lift and drag is to change the camber of the wing. That's used through that's done through all these flight control systems, ailerons, rudder, elevator, and stabilator, in different ways. And then it's also used through those high lift devices such as flap, slat spoilers, and trim devices. And then another review is just all three axes of the airplane. So we have three axes of the airplane. This is figure 2. We have the lateral axis, which runs from wingtip to wingtip. We have the longitudinal axis, which runs straight through the middle of the airplane, from the tail cone to the nose cone. And then we have that vertical axis, which runs from the roof to the floor. It goes straight through. And then just one more time to review lift. Again, it's that differential in pressure. High pressure on the bottom, low pressure going over the top. Lifts the airplane. So for our primary flight controls, we basically have 3 main controls. One for each axis. We have our ailerons, elevator, and rudder. And there's different ways to actuate these flight controls. Cessna 172, for example, if we take a look at our information manual, this is a Q model, but I think it's pretty much the same. It is we go to section 7, which is system descriptions. We got flight controls. The airplane flight controls consists of a conventional aileron, rudder, and elevator control surfaces. The control surfaces are manually operated through mechanical linkage using a control wheel, yoke, for the ailerons, elevator, rudder, and brake pedals for the rudder. So we're using our control wheel for our elevator and rudder, and we're steering with our feet for rudder and brake pedals. But there's other ways to do this. 737, there's a mechanical linkage there too, but it's also hydraulically assisted, because when you're going, Mach 0.78, you can't physically, it's really hard to overcome all that force from the air on those wings. And then newer technology has the fly-by-wire, so it's usually a stick, sometimes a yoke, feeding a computer, and the computer either activates a mechanical motor, or electrical motor, or a hydraulic motor that moves those flight controls. So let's start with the aileron for our 3 primary flight controls. We have aileron, elevator, and rudder. For each of these flight controls, we're going to be asking 3 questions: what, where, and why. So what is it? How does it work? Where is it located on the airplane? And then why does it work? And then how does it work? So for ailerons, what is it? It controls roll about the longitudinal axis. And so I always get confused when it's this controls this axis, but about this axis. So the way I think about what axis the flight control is acting about is the flight control that is not, it's just spinning when you actuate it. So when you turn the airplane with the ailerons, right, you change the angle of bank, and it's spinning on that longitudinal axis, turning the airplane, and it turns the airplane. It turns the airplane by changing the angle of bank, and having a airplane that doesn't bank excessively is lateral stability. Shout out Lance Vaculin for almost getting me on my commercial check ride when I didn't know lateral stability. Where is it? It's on those outer part of the wing, on the trailing edge. So looking at a wing, we got our leading edge, we got our trailing edge. We're going to the back half of the wing on the side, and it's at the outermost part, right? Because when we actuate, we get more leverage, we get more of a moment arm from pushing on the outside compared to pushing on the inside. Why does it work? Because ailerons change the camber of the wing. So looking at the figure, pulling up my PowerPoint, it's the old-fashioned drawing of a 172 or a high wing airplane. I think it's figure 3. Yeah, and that's showing how it changes the camber of the wing. So one wing, ailerons work by one deflecting up and the other deflecting down to change the camber of the wing. Continuing on, the raising and lowering of the wing, like I said, it changes the angle of attack, and therefore creates, it trades This one creates a little bit more lift, but it also trades that vertical component of lift, and we usually count on the vertical component of lift to make the airplane fly. It trades a little bit of that for the horizontal component of lift. That's the thing that actually turns the airplane, because when you get a low horizontal lift, that's what moves the airplane and changes the direction of the airplane. So that's why we lose a little bit of that vertical component of lift, which results in a nose-down pitch, because, as John Mayer taught us, gravity, it's working against us, and makes the airplane fall to the back, makes the airplane pitch down. That's something that we learn about in a steep turn maneuver. And so our ways around that are to either increase the back pressure, increase the power, or both. Specifically to the 172, looking at the PIM section 7, systems, description. When the control wheel is deflected, control wheel is a fancy word for yoke, the steel push rods are activated, moving the ailerons by wire and pulley. So it's the same as the rope on a flagpole raising the flag. You pull on that, the pulley's just deflected around corners, and it's kind of like a little mini cable that push the ailerons to move in opposite ways, right? So this one turning this way, you go down to go up. So this one lowers, this one raises. This kind of creates an unfavorable characteristic that's called adverse yaw. So we know that yaw is the thing that directionally turns the airplane flat on a 3D surface around that vertical axis. Since the downward deflected aileron, which is the downward deflected aileron, makes the airplane raise its wing, produces more lift. When you produce more lift, you also produce more drag. And so that yaws the airplane, because it yaws to the lower drag side, the higher drag side, yawing that airplane in the direction away from which you are turning, which is an uncoordinated turn, and it's slower. So you have to use rudder to counteract that. So when you turn the airplane to the left, you're going to add just a tiny bit of left rudder, looking at your turn coordinator to figure out how much you need, and that'll help you coordinate up for a standard rate turn, or however it'll, your rudder input will vary for the given angle of bank and how much you're turning. The amount of adverse yaw is greatest at a low airspeed, high angle of attack, so going slow, high angle of attack, and with large aileron deflections. So the main time it's your slow, high AOA, and with large aileron deflections is takeoff. So if you're going slow, you have a high AOA, and you turn suddenly, you're going to have a lot of that. And that's why you need a lot of rudder. Well, not the only reason, but why you need a lot of rudder when turning on that initial takeoff turn. There's different aileron types to... sorry for saying too much. Different aileron types to counteract for this adverse yaw. Differential ailerons, which you can find on DA-20s and Cirrus SR-20s, 2s, I think. They, gotta stop saying them. The aileron that is being raised, the aileron that is being lowered to go up, so this aileron travels further than the one being lowered. Right? Yeah. So that equalizes the drag across the board because it increases the drag on the wing that's lower to create more drag. While this helps get rid of the effects of adverse yaw, doesn't completely eliminate them, but it's a way to get a good start and help eliminate that adverse yaw. You're still going to need some rudder when you turn the airplane. So anyone who flies a DA-20 will tell you. There's freeze type ailerons. This is really found on STOL planes, kind of like Kit Fox type airplanes, and that's the aileron that is being raised pivots on an offset hinge It's easier to look at this on the figures. It's figure. Yep. I love when Keynote does not. Come on, Keynote. Figure 5 is a freeze type aileron. And what that does is when it slides back on that offset hinge, right here, a little bit of drag is created from the air flowing, splitting, and going up top to bottom. And so that equalizes the drag. That's on the lowered wing, right? Which is, you need the more drag because drag is coming from that high wing, yawing the airplane away from the turn. The slot also smooths the airflow over the low aileron, making those ailerons more effective at high angles of attack, which is why they're used on STOL airplanes, to have a little bit more controllability when you're traveling that slow. The final way is coupled ailerons and rudder, and that's using mechanical linkages that when you turn the airplane, it'll add just a little bit of rudder to compensate for that increase in bank, and then as you roll out, it'll take away a little bit of that rudder, and so that takes away some of the pilot's responsibility. For a Cessna 172, we have what I like to call voice-activated adverse yaw correction, because as you start to turn, you're not going to be coordinated, and your CFI is going to go coordinate, step on that rudder. You're going to go, oh yeah, and then you step on the rudder and correct for it. Voice-activated, your CFI's voice. Continuing on to the elevator. Elevator is on the back empennage of the airplane, usually, about 99% of the time. The only time that I found it to be not is on some weird experimental airplanes and the Piaggio, which is that weird airplane where the engines push instead of pull. And that has a canard, which is like it's the exact same thing as an elevator, just in the front. For some reason, to be different, maybe. What is it? It controls pitch about the lateral axis. So that lateral axis runs through the airplane, and as we pitch the airplane up and down, the elevator makes the airplane rotate about that lateral axis. And it also controls longitudinal stability. So looking at that longitudinal, how stable it is, how much it paints the sky in front of it when it sweeps back and forth, that's controlled by the elevator. Why? Because when we pull back on that, or forward, pull back or push forward on that control stick or yoke, we're changing the camber of the horizontal stabilizer, like we are with the ailerons when we turn the airplane. Pulling back, it raises the trailing edge, decreasing the camber, and creating more of a tail down force. When we lower the tail, we raise the nose, pitching the airplane up. So when we add our full power on takeoff, we add full power, engine gauges. When we get to our 55 knots in a Cessna 172, we rotate, decreasing the camber on the horizontal stabilizer and the elevator, and pitching that airplane up so we can actually fly. Consequently, when we're ready to descend, we're at our cruise, we pull power, and we push the airplane down. We increase the camber of the wing by deflecting the elevator down, generating a more tail up force, pushing the back of the airplane up, bringing the nose down, creating a nose down pitch attitude. Since it does that because when we lower the tail, we pitch around that lateral axis and the CG to raise the nose. It's kind of like a seesaw almost, where we rotate around that fulcrum. There's a few types of elevators. On a Cessna 172, you're going to find a normal elevator. This 777-200F has a normal elevator too, where you have that horizontal stabilizer, and the elevator can be found on the trailing edge in the back of that. We have a T-tail, and so a T-tail can be found on Where are they found? Dash 8s and even a smaller airplane like the Piper Seminole. There's a few advantages and disadvantages to the T-tail. The T-tail is when, instead of having the horizontal stabilizer and the elevator attached to the fuselage, it's actually attached on top of the vertical stabilizer. This is to it creates uniform airflow in all types of flight conditions across that horizontal stabilizer, because, like I said, for that Dash 8 and that Piper Seminole, there's a lot of induced air going over the wings and onto that horizontal stabilizer in cruise flight and during different stages of flights, but in some other types, in other stages of flight, whether that's nose high, climb, cruise, nose low, or any sort of changing, you're going to experience different amount of induced airflow over that wing, so that varies the effectiveness of the elevator and the horizontal stabilizer. And so to create uniformity and to take the guessing out of, all right, what stage of flight am I in, so do I need more or less to compensate for this, they just put it on the top and then provide some uniform air during each stage of flight. However, because there is no induced air, and that induced air is the air that's sped up as the air flows through the prop, because that prop's spinning, sending faster air out behind it, it can almost make the wings and the elevator feel like they're going faster than they actually are. Kind of like ground speed compared to true airspeed. Because there's none of that induced airflow going over the wings, at lower airspeeds, the flight controls can become more mushy on a T-tail and have less effectiveness, because there's less, the flight controls are behaving like they are at the speed that you're actually going, instead of the speed of the air that was sped up by the props or the engines going over those flight control surfaces. Another type of horizontal stabilizer and elevator there is called a stabilator. That combines both the horizontal stabilizer and the elevator. So instead of just that trailing edge moving, the whole piece moves. That has a downside, which is you're not changing the camber of the wing to change the angle of attack, you're just directly changing the angle of attack, creating either a tail up force or a tail down force. This leads to stabilators becoming extremely, extremely sensitive to even the tiniest of movements, because instead of just moving a tiny little piece of that horizontal stabilizer, you're moving the whole horizontal stabilizer, changing the airflow. And so to compensate for that, which you'll find on a Piper Arrow, is anti-servo tabs. And so that the definition is to reduce sensitivity by resisting control inputs. So what it basically does is it kind of mellows out whatever flight control you're inputting, so you can input more of it, like lessening the sensitivity and making it more controllable and making it more easy to feel out what you're doing before you pull back a tiny bit and you're already, halfway through a 90 degrees nose high pitch attitude. In the Cessna 172, you'll just find the normal horizontal elevator and horizontal stabilizer using pulley and wire system, just like the ailerons. And that can be found on Figure. The description of that, or a picture of the description can be found section 7, obviously. And the picture of that can be found Figure. Should just stay up. I don't understand why it's not. Figure 6. Moving on to our final primary flight control is the rudder and the vertical stabilizer. So what is it? The rudder controls yaw about the vertical axis. So we're turning around the vertical axis. And it controls yaw, which is the direction, the 2D direction of the flight, of the airplane. And it controls directional stability. So as we saw in that intro video, with that Falcon, it was coming in and it was having horribly dangerous oscillations left and right from the yaw. So that's the thing that leads me to believe that the rudder, or maybe the yaw dampener, was affected by that, whatever happened, the emergency. It's located on that trailing edge of the wing. Not the wing, the vertical stabilizer. Just like it is essentially, if you just took this horizontal stabilizer, cut it in half, and then tilted it 90 degrees, took some super glue and duct tape, and just like put it vertically. That's essentially what it does. And why does it work and how does it work? That's figure 7. So we're using our feet to yaw the airplane left and right. And that just changes again. It changes the camber of this horizontal stabilizer, which creates more yawing action on one side compared to the other, and it turns the airplane much like, I think of it like a rudder in a boat. So a boat would be like this. You turn the rudder, and the boat turns on the surface. It's the same thing, but instead it just turns the airplane, instead of on a water, it is doing it in the sky. In the Cessna 172, we have, in most airplanes, you have the normal vertical stabilizer and rudder. The rudder is found on that trailing edge of the vertical stabilizer, and that's through the rudder pedals, pins, and linkages to the pulley wire system to the rudder. On some airplanes like the 172 and the Piper Arrow, those rudder pedals will also turn the airplane's nose wheel through, again, pulleys and wires. And on some airplanes like a DA-20 or even the SR-22, that's completely eliminated. You turn the airplane via braking, and that nose wheel is just a free cast-ring nose wheel that can just spin wherever it wants. One variation on the horizontal and vertical stabilizer can be found figure 8. That's called the V-tail. It's usually found on the Bonanzas. I don't know who else. I think they make a Piper Arrow with a V-tail. And it's very complicated. Not very complicated. It's a little bit more complicated from the normal 3 horizontal stabilizer, vertical stabilizer. Instead of having 3, it just has a V. So you can see that's how they named it. Put a lot of thought into it. And it combines the horizontal stabilizer, the vertical stabilizer, into that V-tail, and then it combines the rudder and vertical and the elevator into something called a ruddervator. Super cool word, fun to say. And the problem with that, or not the problem with that, the thing that makes it a little bit more complicated is that in the flight controls have to determine, when you pitch back, how much of your pitch back to put into changing the bank, or changing the pitch, without disturbing any of that yaw. So it has to, when you turn the airplane and add a little bit of rudder, it has to sum what you did and then split it up between the aileron, not the ailerons, but the elevator and the rudder. They say there's a little bit of a weight reduction because you only have 2 pieces of metal instead of 2, and there's a little bit of a drag reduction because you only have 2 pieces sticking in the air instead of 2. But it's negligible, and the complex summation and distribution system of those flight controls add a little bit of weight, and that kind of offsets any of the advantage of the increased performance from aerodynamics and weight. The only reason that I can see to do it is because it looks really cool, which it does. So if you're chasing after that, get the V-tail. That brings us to secondary flight controls. So now we're shifting our gears from the main ways of controlling the airplane to increasing performance, or a secondary way to control the airplane, which either makes our job easier or allows us to do a little bit more things, or improves the performance of the airplane. We're going to first look at trim. because trim is really important to use, and becoming a master of trim makes your life so much easier when you're flying an airplane. What is it? It's considered to be the poor man's or the poor woman's autopilot, and it's the main trim reason that we have trim is to relieve the constant pressure needed on that flight control to help minimize your workload. So maybe you can let go a little bit, or just not having to like wear your muscles out. I have an uncle who's a captain at Southwest. About 2 years ago, he's taken off out of Houston, headed to Denver, when they experienced runway trim, and so that means the airplane trimmed. It wasn't runway trim. It was the trim locked in place, and so they were trimmed for takeoff, like we trim for takeoff. And so what the trim for takeoff does is it pitches for that nose up pitch. And so when they got to level off and they went to go move those flight controls, they couldn't. It was too much for the autopilot to overcome, and so they spent about 40 minutes in the air with a special bracing position because they kept having to move those controls full forward because the airplane just wanted to have that nose up pitch attitude because that's what the trim was telling it to do. They eventually had to declare an emergency, turn back around, and it was about an hour flight, and he said his arms had never been so tired. And we don't want tired arms because I'm lazy and I like to do as little as possible. So what we use as trim is that as we level off, that airplane still wants to climb because we set that trim for takeoff. As we level off, we need to maintain that constant forward pressure on the control wheel, and so what we do is we trim the airplane a little bit nose forward, which means we nose forward, we need to bring the nose down, which means we need to increase the tail up force a little bit to be able to maintain level flight automatically. And how does it maintain level flight automatically, or how does that trim system even work? It's pretty uniform across most airframe types. We can look at the figure on the PowerPoint. It is figure figure 9. And so we have those trim tabs. So you can see the trim tab is basically the back half of the elevator. On 172, it's looking at the back of the airplane like this. It's going to be found on that right horizontal stabilizer / elevator. And it's just a tiny little thing that can, it's basically a tiny little elevator that you control with that trim wheel and trim the airplane by changing the camber of the wing for whatever system or whatever stage of flight you're in, whether that be cruise or takeoff or descent. It really becomes second nature as you start to fly more because you don't want to have to constantly fight to maintain your altitude and your correct pitch attitude. So, during that cruise phase, you get your reference points. You'll pick your reference points on the horizon. You'll say, all right, that's about a level trim. And then you feel how much pressure you have, and then you just trim that control pressure out of your hand. For other things like climbs and descents, you can just set the airplane to an airspeed, like a VX climb or a VY cruise climb, and then just trim till you can let go of the control wheel, and it just holds that airspeed for you. There's a few different types of trim that we have. We have the main type is the balanced trim, and so the trim tab movement is not just coupled to whatever you roll in on that trim wheel. It's coupled to whatever input you add through the flight controls, because as you change that camber of the elevator, you also need to maintain that same relationship with the trim, because having a nose up trim and then raising the nose, those two forces will add together when really you want the airplane to behave. You want to be able to control the airplane with the same effectiveness, no matter which stage or which trim you're in. And so that balanced trim, which is the type of trim pictured in Figure 9, as you as you increase that back pressure and they create to pitch the nose up, creating more of a tail down force, the trim will move opposite of that to balance that out. And then on the opposite, we have the anti-servo trim tab, which we kind of talked about with the stabilizer because it's found on a stabilizer. And it's the same as the balance trim. It moves, but instead of moving the same way, it moves, correction, balance trim moves the opposite way of which you move the control wheel. The anti-servo trim tab moves the same way because you need, like we talked about for the horizontal stabilizer, to resist those control inputs. And so an anti-servo tab combines the anti-servo trim combines the trim tab with an anti-servo tab to balance out the trim and be able to have trim, and then also to resist those control inputs. And then the last type is the ground adjustable, and that's found on 172 for the some, I think Westminster's airplanes has those, or at least the airplane that I got my private in had ground adjustable, so it was just basically a flimsier piece of metal on the trailing edge of the rudder, and you could it's really just dialing it in by trial and error. So if you take off, you have a lot of left-hand turning tendencies, and those continue throughout the flight. You can just add a little bit of that right trim to kind of balance out that yaw, and that's just done by bending the metal, and done by trial and error, mostly error. There's a few problems with trim, and that can be the elevator trim stall. And so say you add, say you're coming in and you nose the airplane, you set trim really far back, you know, it's less effective and you're going slower airspeeds, and then you go around on an approach, you add that full power, which means the nose wants to come up, and the nose with full back trim really wants to come up. You would stall the airplane, especially on an approach low to the ground. That could be a problem. Stalls are never fun, as we all know. So that's trim. It's just used to, it's that poor man's autopilot, and it's used to relieve control pressures throughout the airframe or throughout the flight, and make it so you can not have to worry about the basic flying tasks so much, and be able to, you know, do other things around the cockpit without having to devote so much of your mental and physical energy into actually controlling the airplane. The other type of secondary flight control we have is the high lift devices. And usually these high lift devices are used to increase or decrease lift for different phases of flight. And they're usually located on the wing, right, because that's our main source of lift for the airplane. And they can increase lift and increase drag. Usually high lift devices are used during takeoff, approach, and landing when you want more lift at slower airspeeds. And you want better economy during cruise, so it means you want less drag, so you want less lift to have less drag, and you want more lift and more drag during approach and landing. So these high lift devices are the things that meet those two needs in the middle and say, all right, we can use these during that approach and landing and takeoff phase when we need that lift and drag, but when we want to put that drag away, we can put also those high lift devices away and store them basically in the wing. And so high lift devices are broken down into two areas. We have our leading edge, which is that front of the airplane, front of the wing devices, and we have those trailing edge devices. The main type of trailing edge device and the main type of high lift device in general are our flaps. And this is now jumping into figure 10. They're attached to the trailing edge of the wing on the inboard side to make room for those ailerons on the out. They're found throughout here. And they really have three main functions. They permit slower landing speed and decreased landing distance. They help you, they allow safe obstacle clearance through having a steeper angle of descent with the same speed, because you want to land at a slower speed. You don't want to bomb it in at V&E and then have to run all that airspeed off on the ground. And they, it's more controllable at an airspeed, because as you slow down, your control surfaces are not as, there's less air going over them, so you have less air to manipulate and change whatever you need to change. And so it's more safe and controllable on approach and landing. And then again, it's more economic in that cruise phase. We have four types of flaps, four basic types of flaps, and we have, each type of flap have different variations. We have that plain flap, which can be found on, I think Piper Arrows have the plain flap, and that's essentially just, you have a wing, back half of it comes down. You increase the camber, right? So flight controls, if you take one lesson away from this, is that to control the airplane, you just change the camber of the wing, because changing the camber of the wing changes the angle of attack. Changing the angle of attack changes the lift created. And so when you increase the camber of the wing, you have a significant increase in the coefficient of lift for each given angle of attack. So at the same angle of attack with your flaps out, you have an increased camber. And so you're creating much more lift for that angle of attack. When you increase lift that much, you also increase drag. And for flap types, you have varying degrees of flaps. You can have 10 degrees, 20 degrees, 45 degrees. And it's generally thought that you increase lift and drag, and then as you continue to extend those flaps closer to 45 and eventually 90 degrees, the increase in lift goes away, and it's more of just a parasite facing the wind going down. Going down is in increasing the drag. Continue on, we have the split flap, which we have our airfoil here. Our split flap just extends out of that airflow. And so what does that do? It deflects air down, and it has a slight increase in lift, but the main advantage of the split flap is that it has way more drag, because as that air, say air is coming this way, as that air is coming like this, and that is extended down, the air is split, and air wants to meet uniformly, right? It wants to do like in a basic section of a wing where it comes back together really nice. That's what air wants to do. So when it's deflected like this, it's broken up, it wants to backfill over here, and it creates much more drag. It creates more drag than, there's a greater increase in drag than a greater increase in lift for the plain flap. And so those are used not very often, because it's not, you want to increase lift as well as drag. So that's why they invented the slotted flap, which is what a Cessna 172 has, and that is by far the most common flap on all aircraft, because it's used by the Cessna 172, it's used by the 737, it's used by the 747, it's used by the A380, it's used by the 777-200-F, and it's a significant increase in lift compared to split or plain flaps, because when the best way to do this is to look at the illustration on figure 10. When we have that slotted flap, split flap disturbs the air so much. The advantage to the slotted flap is it decreases the disturbance in the amount of air. So it promotes good lift. When the slotted flap is lowered, high energy air from the lower surface is ducted to the upper flap surface. The high energy air from the slot accelerates the upper surface and delays that airflow separation that is so common in the split flap, providing a higher coefficient of lift. So it really it acts as more of a wing as well as a high drag device compared to the plain flap or the split flap. Larger aircraft like the 747 has triple slotted flaps, so you have 3 different slots in it. So that provides even more lift, because there's more places for that airflow to not be disturbed and for more places for lift to be generated. And the final type of lift is, I don't have a figure for it, is the Fowler flap. And that Fowler flap is very similar to slotted flaps, except for instead of the first thing being increasing the deflection of those flaps, it actually first slides back on rails, increasing wing area and increasing lift significantly more than drag. So these can be found on backcountry airplanes and anywhere where you need large lift increases and not a lot of drag increases. And so it significantly increases wing surface area and wing camber by traveling back on tracks and then deflecting downward. So there's a huge addition of lift and then a huge addition of drag. The Fowler flaps, like I said, more backcountry airplanes. I met a guy who once said the Cessna 172 has Fowler flaps because when you fully extend them, there's like a 3 millimeter difference between the leading edge and the trailing edge. Take that with a grain of salt. According to most sources, they have Cessna 172 has slotted flaps. Fowler flaps is when they actually slide back on tracks. There's different ways to control flaps. There's the manual way, which you'll find in like a Piper Arrow, where you basically just pick up a lever and then just it cranks those flaps down just via mechanical pin and lever, like you would ailerons and rudder. In a Cessna 172, you usually have electronic, so there's a little flap switch on the flight control, usually over by the right seat, and you can just select your flaps there, and then an electronic motor is the thing that actually lowers those flaps. And then on the bigger airplanes like a Boeing 737, it's actually hydraulically actuated. Hydraulically actuating those flaps down and creating more lift and more drag. Continuing from the trailing edge to the leading edge, we have leading edge devices on several types of airplanes that also increase lift. On STOL airplanes, there's these things called fixed slots. And so a fixed slot is basically like a second leading edge that's bumped out in front of the airframe. I wish I had a picture of it attached to the PowerPoint, but it basically creates it directs airflow over the upper wing and delays that airflow separation over the wing that you get when you have a high angle of attack, right? Because then you exceed that critical. It allows you to, I think I read somewhere that a normal airplane stalls at around 15 degrees nose up from normal cruise. I think it said 12 to 15 degrees. With fixed slots, you can go from 15 degrees nose up to about 25 degrees nose up because it creates.
Hey guys, this is Scott Adams with Efficiency.
Because it creates, it allows for more air to go over those wings and delays that airflow separation. That is the thing that kills the lift. Again, that's found on STOL planes. And then finally, we have the movable slat. And so this is usually found on bigger airplanes like the 737, the A320, and it can be automatically deployed at low airspeed. And so a slat is much like a slot. I know it's confusing, slot, but the slat can be extended. The big difference is that the slots are fixed and the slats can be extended, and they basically do the same thing, right? They lower the stall speed and allow for a higher angle of attack. And the big difference is the slots are movable, right? And so airliners use these slots to they're tied to the flap operators, and so when they extend the flaps beyond a certain point, those movable slats on the leading edge come out too, to be able to create more airflow. They also change a little bit the camber of the wing, so that also increases lift. All right, so that just about covers everything that we need to go over. And so let's just do a little review. We have our three primary flight controls, right? We have ailerons, rudder, and our elevator. Our ailerons turn the airplane by, just a general review, right? All flight controls mainly change the camber of the surface that they're actuating or that they're attached to be able to have that desired change in lift, which then changes whatever you need to do. So right? We go down to go up to turn the airplane, lowers one side, raises one side, creates more lift on this side than this side. That turns the airplane because of that horizontal component of lift. Then again, we have that adverse yaw, so we have to compensate for that with rudder. Some airplanes have those differential ailerons or freeze type ailerons or those coupled ailerons and rudder to be able to compensate for that, but usually you're just going to have to step on the ball, coordinate your turns. We have that elevator, which operates the same principle as ailerons, except for instead of turning the airplane, it pitches the airplane up and down by either increasing or decreasing the force on the tail. Since we pitch about that lateral axis, increasing the tail down force pitches the airplane up, and decreasing the tail down force pitches the airplane down. And finally, we have that rudder, which controls directional stability and can change the direction, yaws the airplane left and right, again changing the camber of the wing to compensate and yaw the airplane around. That's our primary flight controls. We have different types of elevators with the T-tail and the stabilator. We have basically one type of vertical stabilizer. We have that V-tail that has the ruddervator, super fun to say. And then we have our secondary flight controls, which just supplement those primary flight controls, make our airplanes safer, more economical, and easier to fly. We have our trim, which is a mini control, elevator trim is basically a mini elevator that is used to control the pitch of the airplane and relieves control pressure, so we don't have to constantly fight those controls. We have the balance trim, which helps the airplane compensate for when we change the flight controls. It'll change the trim to match that change in flight controls so that we get a uniform behavior of the trim for all of our inputs. We have that anti-servo trim tab, so on that stabilator we need to resist those control movements because the change in the tail up or tail down force is so strong. We need to resist those so that we can actually control the airplane, and so those anti-servo trim tabs combine those two. We have that ground adjustable trim tab, which you use on the ground to make small changes in the trim, usually found on the rudder and ailerons, but mostly the rudder, and that's just bending a little piece of plastic. It's much simpler than the name leads on. Then finally we have those high lift devices that are found on the wing, that increase lift and drag, right? Because when you increase lift, you increase drag. And those are mainly used for takeoff, approach, and landing to allow for slower airspeeds, higher descent angles, and better economy during cruise. We have they can be found on the trailing edge, the leading edge. Our most common type is flaps. We have plane flaps that just come down, our split flaps that extend from the bottom, and because of that, just really disturb the air on the back half of the wing and creates much more drag. We have those slotted flaps, which is the main type of flap because it has such a good increase in lift as well as drag, and that has so many benefits because we also want to increase lift. Because it doesn't disturb that airflow the same as the split flap, it helps that air stay together over the back half of the wing, over the flap, and then outward as the downwash downwash. And then finally we have those Fowler flaps, which first slide back on rails to increase wing camber and wing area, and then extend downward. The big advantage to that is that you have small drag increase as that wing area increases, and then the bigger drag increase. Remember that it's not proportional, so as you increase drag, you increase lift initially, and then that increase in lift goes away. That's like on a Cessna on a short field takeoff, you only use 10 degrees of flaps, because anything beyond that, the penalty of the drag outweighs the increase in lift that we get. But on final, we use full flaps because we want to have the most drag possible. There's different ways to control the flaps. You know, we have different amounts, 10, 20, 35 degrees. We have the manual way, clicking it through, like you'll find in an Aero, electronic, like you'll find in a Cessna, and hydraulic, like you'll find in a Boeing or an Airbus airplane. And finally, we have those leading edge devices, which the same way that the slotted flap works, it helps promote smooth airflow of air over the wing. Those fixed slots provide different channels of air to go through the wing. Instead of just all the way over the wing, you can go through the wing when you're at a high angle of attack to delay reaching the critical angle of attack, or to make that critical angle of attack higher in terms of pitch attitude to the horizon. And finally, we have those movable slats, which are found in airliners that are usually tied to flap operation and can be deployed by extending those slats outward and increasing the lift on the leading edge as well as the trailing edge. Alright, you guys, thanks so much for sticking through this, and I'll see you guys next video.